All right, guys. Welcome to episode 2 of functional analysis, and in this very episode, we'll be discussing norm spaces. So, the a norm, as stated earlier, is a vector space that measures the length or the magnitude of a vector. So, and now for a function to be a norm, it must follow three golden rules. The first is the positivity. The length of a vector is never negative, and the only vector with zero length is the zero vector itself. So the second rule is that if you scale a vector by a number, the length is scaled by the absolute value of that number. And thirdly, for the third rule is called the triangle inequality. So the length of the sum of two vectors is at most the sum of their length. So you can think of it like walking directly from point A to point C, and you notice that you can never go from A to B and then B to C. So every norms creates a natural way to measure distance, turning the space into a metric space where the distance between the 2 points is just the norm of their differences. Now when you see R2 simply means two dimension. So this is a typical example of Euclidean norm. So you can see it is two dimensional. So that's the meaning of the R2 there. So you are taking the length of a vector space. So that's a typical example of R of Euclidean norm. So under types, I'll be explaining only Banach space. Now, if don't forget that we said a norm is a space, a norm space is simply a vector space with a norm, but it may and it may not be complete. If it is complete, it simply means that every Cauchy sequence will converge to a point inside the space. So we call it a Banach space. For example, Rn, that is when it is dimensional, in finite dimensional norm space, all norms are equivalent, so they are always complete. So in R dimensional, if it is R dimensional, the Euclidean norm is therefore called a Banach space. So for function spaces, there are also norm spaces where the elements are not just numbers or sequences, but they are functions themselves. So in a function space, each function acts like a vector. So we can add them, scale them, we can measure their size using norm. Are you getting it? So that is a function space. So we have different functions representing that acts like a vector space. That is what we mean by a function space. So when we say a norm is equivalent, two norms are called equivalent if there exists a positive constant, two positive constants. This means that one can be bounded above and the other one can be bounded below. So the operator norms tell us how much a linear transformation can stretch a vector in the worst case. Suppose T, so you can see operator norms. Now we have dual spaces. So in functional analysis, the dual space of a norm space captures all the ways you can measure or probe that space using continuous linear functions. So dual spaces are powerful because they reveal hidden geometric and analytic structures. So even in finite dimensional spaces, the dual space has the same dimension as the original space, and every linear function can be expressed as a dot product.